Okay, on to example number 3. Determine any maximum or minimum values of y equals x squared ln x. When we look at this function, you should be automatically thinking, well, max or min, I must set the derivative equal to 0. Looking at this function, x squared ln x, means that we're probably going to have to do the product rule. So, set the derivative equal to 0 and use the product rule. Here are your two pieces. X squared is one of the pieces, and the other piece is ln x. So if we consider this the first piece, we need to take the derivative of this piece, which is 2x, times the second piece, which is ln x, plus the first piece times the derivative of the second piece. The result here, now before I forget, I want to show you how this question, seemingly easy, could be expressed in a form that looks a lot more difficult. For example, try y equals ln x to the power of x squared. What would you do then? Well, folks, you know that the ln rule says that we can take the exponent and bring it to the front, and that turns out to look exactly like this. So it's important to note that a question seemingly easy could be, or seemingly difficult, really you need to apply just some ln or logarithmic rules to get the question in a form that you could find the derivative. Anyways, let's keep going. So 0 equals, now we need to common factor. What are we going to common factor out is an x, and we're going to be left with 2 ln x plus 1. Well, that means that we have two values for when the possibility of this derivative equaling to 0. One of them is x equals 0. The other one is when 2 ln x is equal to negative 1, which means that ln x is equal to negative 1 over 2. That means x is equal to, you change this ln into an exponential. Ln of base, it's a log base e, so e to the power of negative a half is equal to x. That is the exact value. The approximate value, just so that we could get a number later on, folks, is 0.6065. We need the number for our test points because we have to test if there's any maximum or minimum. So we're going to test it out by determining the intervals. So we have intervals from negative infinity to 0, 0 to e to the negative a half, and e to the negative a half to infinity. So we pick values, negative 10, 0.5, and 10. You find out that f prime of x, so the function, is non-existent in the first interval. Why is that the case? Well, looking at this right here, this interval, let's say negative 10, if I plugged it into the derivative equation, that's not a problem. But here would be a problem because you have to think about it. This is a ln base e. E is a 2.718. It's a positive base. When can a positive base have a negative number? The answer is never. Therefore, it doesn't exist. If we pick a value of 0.5 or 0.1 or anything between 0 and e to the negative a half, you're going to get a value that's less than 0. So we have a decreasing function from 0 to interval. Then we have an increasing interval from e to the negative a half to infinity. So it goes from decreasing to increasing, which means there must be a local minimum at the point e to the negative a half and something. So let's find that y value. E to the negative a half, all squared, times ln of e to the negative a half is going to equal, now let's look at this, folks. When you square this out, this will give us e to the negative 1. Ln of e, we know, is 1. We bring this to the front of it, and we end up with a value of e to the negative 1 times negative a half. So that works out to be negative 1 over 2e. And then we can change, since we already have this with a positive exponent, we can change this so that they're both positive exponents, and that becomes 1 over e to the half. So 1 over e to the half, comma, negative 1 over 2e is the exact value And this turns out to be a local minimum. All right, next. So this, again, is a local minimum. Is a local minimum. All right, let's go to the next one. Oh, here's our homework. This is the homework in this section. We don't have any homework assigned in the homework pages because this is extra homework questions for you to try. Go ahead and try these. Now I'm going to show you some homework examples that we're going to take up. These homework examples are questions that I recommend that you work through and make sure you have an understanding of how to approach them. In the first one, it was a question taken from the textbook, and you're asked to evaluate f prime at 5. And this is question number 5b. Evaluate ln of the function at the derivative of this ln of this function at f prime at 5. So, what does that mean? Well, we take the derivative first. But before we do that, remember the ln rules. The ln rule says that if I have the ln of a quotient, I can take the subtraction of the individual lns. By doing that, this helps us get the answer a little bit easier. We do that because then we don't have to take the inside here, with the quotient rule. We don't want to use that if we don't have to. So what we can do is now convert it so that it's a difference of the numerator, ln of the numerator, minus ln of the denominator, and we can take the derivative now. That turns out to be the derivative of the inside times 1 over t minus 1, minus the derivative of the inside, which is 3 over 3t plus 5. And from there, we can find a common denominator, but we don't need to, folks, because we need to find the derivative of at x equals 5. So we just plug in, at t equals 5. So we plug in t equals 5, and you end up with an answer of 1 over 10. So f prime at 5 is equal to 1 over 10. All right, that was the answer to 5b. Let's look at another one. So this was 6c from one of the homeworks you've had assigned. And here it is, and you're asked to find the derivative. Before we do that, we convert it so that it is in division statement. So instead of using product rule, we're going to use quotient rule. We set the derivative equal to 0. So same as the previous one where you have to find what values will make it equal, what critical values, what are the critical points. Or maybe it could ask you, for example, for which values is a maximum or minimum. In the meantime, you still have to set the derivative equal to 0 and find the derivative. So the derivative of this top part over here, folks, so we're going to take the derivative of this first using quotient rule, which is 2x over x squared plus 1 times the bottom, all right, minus the top times the derivative of the bottom. Derivative of the bottom is 2x times the top. From that, what you're to do is take the bottom and square it. When you do that, you need to realize that this x squared plus 1 over here will cancel with this x squared plus 1 over here. So you're left with just 2x here minus 2x times ln x squared plus 1. So 2x can be common factored out, and we're left with, once we common factor out the 2x, we're left with 1 minus ln of x squared plus 1 all over x squared plus 1 squared. We set it equal to 0. We find out that x equals 0. The other option is when ln x squared plus 1 is equal to 1. And once you do that, you can convert this ln expression into an e expression. So looking up at the top here, you can see ln of x equals y is equivalent, e to the power of y is equal to x. So by doing that, we can convert this down here, what you see down here, 2e to the power of 1 is equal to x squared minus plus 1. Once we have that, you can then move things over, find out that x equals plus or minus root e minus 1. So, what that means is that f prime of x is equal to 0 when x is equal to 0 and when x is equal to plus or minus root e minus 1. All right, next one. This is one of the questions that you had in the book, and you were asked to find the derivative of this. And it can be quite nasty. So what I did is I changed the u to be in a different color so you don't confuse it with a 4. hu is equal to e to the root u ln root u. What does that mean? Well, we take the derivative with respect to u. So we take the derivative of the first, which is 1/2 u to the negative a half, e to the root u, because e to the power stays e to the power after you take the derivative, and they just do the derivative of the power beside it, times ln u, root u, and then you're going to, because we're using the product rule, we need to take the derivative of the second now, so plus e to the root u, which is the first, times the derivative of the second. Well, the second has a numerator of 1/2 u to the negative a half, that's the derivative of root u, over root u. What does that mean for us? Well, I'm going to pull some things out to make things a little bit easier. For example, I'm going to take out a half, because both of these, here and here, are a half. The next thing I'm going to pull out is root u. Now, where did that root u come from? Well, it came from u to the negative a half. Both of these have a u to the negative a half. So I converted it back to a root, and I brought it to the bottom because it's u to the negative a half. And then what are you left with? You're left with e to the root u. Oh, where did that e to the root u came from? Well, folks, it came from this one, and both of these. It's both there. So we pull that out. So we have e to the root u over 2 root u times what's left. Well, we pulled out the half. We pulled out this half. We pulled out the u to the negative half. We pulled this all out. So all of this is pulled out. You're left with ln root u. Plus, all of this is pulled out. So you're left with 1 over root u. Well, this isn't simplified further enough because really this root u should have been pulled out along here. So we're going to pull it out and you get h prime of u is equal to 1 over 2 root u. Oops, let's rewrite the question because we ran out of room. And we get h prime of u is equal to e to the root u over 2u. Where did that come from? Is I'm pulling out this root u from everything. So root u times root u gives you u. Let's make sure they're in different colors. And then what you're left with inside is root u, ln root u, plus 1. And if you were to find the zeros, you can then it becomes a little more trickier. But at this point in time, that's as far factored as I would want you to get. All right. And that's everything, folks. Have a great night.